coming in at number 1 of Polynomial's greatest hits, we have a very interesting property that is true for all polynomials. The matter of it is, given a polynomial p of x of degree n, that is expressible as the following: a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way down to a sub 1x plus a sub 0. So this is our general polynomial, and it can be any kind of polynomial whatsoever where n is an integer and all of those a values, a sub n minus 1, all the coefficients are complex numbers. Then we know, interestingly enough, that the sum of all the complex roots equals this quotient right here. Another way of putting this would be to say the sum of all the roots of a given polynomial can be found just by looking at the first two coefficients. In other words, the leading coefficient, a sub n, and the coefficient of x to the n minus 1. But perhaps more importantly, this shows a rather elegant connection, or a pattern, that amazingly enough works for any possible polynomial that you can think of. And why is this true? Well, let me show you. So I did some kind of exploration on my own, and generally speaking, this is another way of writing or stating the theorem here. So given a polynomial of this form, where all of the a sub k, all of the coefficients are complex, the theorem is that, of course, the sum of all the roots is equal to negative a sub n minus 1 over a sub n. So it's given by this concise formula, which is very interesting. The proof is that basically we can consider, and I will admit this isn't completely my own proof. It was inspired by a mini course that I took, but it's still very interesting. One of the basic ways of proving this is that we can consider p of x as being just a product of basically x minus r sub I, so a product of binomials. A part of this is that we know this basically from the fundamental theorem of algebra. Because all of the coefficients are complex, we know that there must be exactly n complex solutions to the polynomial itself, and therefore there are exactly n roots. So we can define r sub 1, r sub 2, all the way up to r sub n as being the n complex roots of a polynomial. And so that's very interesting. We make use of this fact because we're basically multiplying out each binomial that represents each root of the polynomial. And we can actually consider a proof by induction that establishes this rather well. First things first, let's consider a general monic polynomial for simplicity. And this means that the leading coefficient equals 1. So a sub n equals 1. And I mentioned it was a proof by induction, so what we can do is actually consider a base case, which would be n equals 2. Or at least I think that's a very useful case to use for our base case. And that is simply because we have just a quadratic polynomial, which we're all familiar with. And we will additionally assume, just to start with, that it is a monic quadratic. So, as a result, we can simply say that p of x must be equal to x squared plus bx plus c. We also know that this must be factorable over complex numbers, so we know that this must be equal to x minus r sub 1 times x minus r sub 2 for some complex roots r1 and r2. However, if we just expand the right side of this equation, what do we get? Well, we know that p of x must be equal to x squared minus r1x minus r2x plus r1, r2. Simplifying further and combining like terms, we can get x squared minus r1 plus r2, that quantity, times x, plus r1, r2. And so, as you can see, analyzing this, we know that, this polynomial we end up with has a leading coefficient 1, obviously, and a sub n minus 1, the next term, so to speak, is equal to negative r1 plus r2. From this, we can deduce that, at least for this basic case, so a sub n minus 1 over a sub n equals negative r1 plus r2 over 1. So r1 plus r2, the sum of the roots, equals negative a sub n minus 1 over a sub n. And it helps to consider, I think, what happens when we move to the case n equals 3. So we just saw that, for the case n equals 2, we expand out, we get x squared minus the quantity r1 plus r2 times x plus r1 r2, so the sum of the roots must equal negative a sub n minus 1 over a sub n. Now the case where n equals 3 is where things get interesting, because we have, for a third degree polynomial, assuming again that it is monic, we have a product of 3 roots, or a product of 3 binomials, because it must have 3 and only 3 complex roots. So expanding out, we can actually get the same general form of a polynomial as in the case where n equals 2, this whole structure right here. And it's being multiplied by a third binomial, which represents the third root. So, expanding this out afterwards, we end up with, we multiply each term of this entire quantity by each term of the latter quantity. So obviously we end up with x cubed minus the quantity r1 plus r2 times x squared plus r1 r2x minus, and after expanding out, we get this whole line right here that directly follows it. What you'll notice is that the only terms in this entire expansion that have the degree of x being equal to n minus 1, or in this case 2, are this quantity, or this term right here, minus r1 plus r2 x squared, and we also have an additional one right here, which is negative r3 x squared. And so combining these two terms, we actually end up with negative r1 plus r2 plus r3. That whole sum times x squared. So what we're showing, and I have a more detailed proof below, in the end what we're showing is that every time we multiply this monic polynomial by yet another additional root, we keep summing all of the roots and adding the next additional root to basically the coefficient of x to the n minus 1. And so again, you can see this more detailed proof if you like, but basically I'm just showing that through induction, if we know that the sum of the roots is equal to negative a sub n minus 1 over a sub n for q of x, which is our previous polynomial, then just by multiplying by another factor that is of the form x minus r sub n, because, the next polynomial that could exist, in other words, a polynomial that is 1 degree larger, must have one more root. So we just represent that by multiplying by another binomial. If we expand that out, we see that we have to add the next root, or the magnitude of it at least. I mean, I know it's negative, but we're adding the value, or the magnitude of the next root, to this sum. And since p of x equals, since the new polynomial equals the old polynomial times x minus r sub n, so it has one additional root, we can simplify this, and we always end up with a final coefficient of a sub n minus 1 being equal to the negative of the sum of all the roots. And from here, correct me if I'm wrong, but I'm fairly sure we can multiply p of x, this new polynomial, by any given scale factor, k. In other words, generalizing it to make it not always a monic polynomial. And in any case, if we're just sort of multiplying through, or, equivalently, I guess I could have said, if we have a polynomial that isn't monic, and it's of the form kx to the n, then all we would have to do is factor out that k from the entire polynomial. And we can do that with complex numbers, because it's a closed field, so we can divide each coefficient by k. And then we'll have something of the form, well, it'll be k factored out from a monic polynomial. And what we're just showing is that, of course, for any monic polynomial, the coefficient of x to the n minus 1 must be the negative of the sum of all the roots. I know that's a mouthful, but hopefully that's clear. This a sub n minus 1 equals the negative of the sum of all the roots. That's the main point here. Because even if it weren't a monic polynomial, even if the a sub n, the value of a sub n, were different, then we could still be able to factor that out and get a monic polynomial for which this must be true. And so this is just what I'm trying to demonstrate here. We find out that this is the sum from I equals 1 to n of r sub I. So it's the sum of all the roots, is what this formula will always represent in any given polynomial. And another finding that I made was that a sub 0 also has a rather special property. Again, correct me if I'm wrong, but the other finding is that a sub 0 keeps getting multiplied in this whole process of induction. A sub 0 keeps getting multiplied by negative r sub I. So in the general case, we should have negative 1 to the n times the product of all the roots. At least up to scalar multiplication. So again, in this whole inductive process, we assumed that the polynomial was monic, and so it might not be the case. But again, even if it isn't monic, we can factor out a constant from each of the coefficients, just factor out that constant, k, so to speak, and then after factoring it out, we know that the value of a sub 0, after doing that, must be of this form, negative 1 to the n times the product of all the roots. So, in other words, for the degree 1 polynomial, we have x minus r sub 1. It's just degree 1, so it's rather simple. So the constant of that polynomial is negative r sub 1. For the case n equals 2, we have, as I showed you before, it's going to be positive r1 times r2. That's just how it expands out. And if we were to continue doing this for the case n equals 3, we can see that the product is actually equal to negative r1, r2, r3. So the product of all the roots times negative 1, because it's an odd degree. So that's just another finding, another discovery that I wanted to share with you, because I thought it was rather interesting. And in fact, we may be able to view this as a kind of generalization of the commonly known properties of monic quadratic polynomials. So getting back to what I showed you before, here's that demonstration of the case where n equals 3. We know that this constant of the entire polynomial after expanding it is equal to negative r1, r2, r3, just like I said. So it does follow that pattern, at least assuming the polynomial is monic. But again, even if it's not, there's a similar pattern. It's just the constants multiplied by a scale factor. So anyways, my point is, many of us were taught in school that when we have x squared plus bx plus c, so something of this form, then assuming it is factorable over real or rational numbers, then b must be the sum of the roots, which it is, and c will be the product of those two roots. So again, many of us were taught even back in grade school that for a quadratic polynomial, if we have this statement, x squared plus bx plus c, and we're trying to factor it into the two real roots or rational roots or whatever, then b will be the negative of the sum of the roots, and c will equal the product of these two roots. However, what many of us aren't taught is the larger, wider view of things. In fact, when we have a polynomial of any integer degree n, then the quantity negative a sub n minus 1 over a sub n will be the sum of all the roots, and the product will be plus or minus a sub 0. So that's the kind of generalization of what you might remember from grade school. But this is much, I think you'll agree, this is a much wider view of it. So again, thank you very much for watching. I just wanted to share this because it's a polynomial greatest hit. I'll see you all next time.